Bismillahirrahmanirrahim. Assalamu alaikum. Okay, welcome back. We got disconnected again because of the light load shedding issue here. So let's quickly recap what we've learned till now, and then we'll try to quickly go over to this first chapter. Hopefully this time we'll be able to complete it, and then probably we'll have to cut our session short today. Okay, so we learned about let. We also learned about it yesterday as well in the Clojure workshop. Okay, let basically binds a symbol to a value. It's kind of like a local binding, or if you come from C++, Python, etc., then it's a local variable binding. And then we learned a little bit about functions and how they can be declared. Here this is an anonymous function which takes a single argument x, and then here it performs some action on that argument x, and basically here it's incrementing it by 1. So if we pass this function an argument of 2, then it would increment it by 1 and it would print out 3. And apparently there's a shortcut or shorthand for writing functions, which is # and then wait, let me yeah. So this is equivalent to function which takes an argument x and adds 1 to it. So here the argument is represented by this percentage sign. First argument, by default this is the first argument, and if we want multiple arguments then there's an option of percentage sign 1 and percentage sign 2, so we can use that. So this is shorthand for anonymous functions. Here we're defining a variable burrito and assigning it a value of this function, which is a shorthand function which returns a list containing beans, the argument that was provided, and then the third element in the list would be the cheese. So if we call burrito and give it the argument of carnitas, then it will return this list. Got it. And yeah, now they're telling it how to name a function. They'll probably tell it. So here we're naming the function x, which multiplies the argument by 2. They're naming it twice using the let syntax, and then they're adding twice 1, the result of twice 1 and the result of twice 3. So this is 1 plus 6. Okay, no, this is 2 plus 6, which is 8. So 2, this will be 2 multiplied 1 will be provided here, so this would be multiplied by 2 and 1, so this is 2 times 1, which would be 2 in this case, and here it would be 3 times 2, which would be 6, and then we add those together, which is 2 plus 6, which is 8. Yeah, here is basically explaining why we use functions to reduce the redundant expressions and isolate common patterns of computation, etc. Now let's see what are vars. Okay, now there's a new concept that will be introduced called a mutable variable, and we use defs for that. Yeah, we learned about it yesterday as well. So let is for local binding. Here twice is only defined inside this block, but if we use def cats 5, and then we can also use it outside this block as well. For example, def cats 5, and now if we call cats, it will return 5, while before, for example, if I call Adam, it would be a syntax error. But now if I define Adam to be 13, and now it will return the value that is bound to this symbol or variable Adam. That's how we define variables or mutable variables. Yeah, and the type of this variable is long. The type of this value, it would apparently this would calculate or evaluate the type of the value that's present or bound to the Adam. But if we want to see the type of the symbol Adam, then we'll have to do this, and this is a clojure.lang.var. So before the value 13, that's defined in Java, it's being used from the Java language, java.lang.long, it's a long, and here it's a construct of Clojure language, clojure.long, and it's var. So vars, like symbols, are references to other values. When evaluated, a symbol pointing to a var is replaced by the var's corresponding value. Var is a shortcut for a variable, if you're wondering. Okay, so before we thought, that ink is a symbol that refers to a function in the Clojure language called ink, but apparently it's ink is referring to, where is the, I guess it's the same thing, no? The symbol ink points to the variable ink, which in turn points to the function. Wow, will resolve. So for example, ink, this is clojure.core.incorporated. ink, the symbol, and if we resolve the symbol incorporated, increment, then it points to clojure.core.incorporated. Oh, sorry, incorporated, not increment. Okay, this is the symbol, this is the variable, this is the whole variable, and if we evaluate it, then this is the function it's pointing to. Okay. Symbol points to the variable, which in turn points to the function. Unlike the symbol, we can change the meaning of a word for everyone globally at any time. Deaf astronauts. This is an empty list. Count astronauts here, deaf astronauts this, count astronauts. Had two distinct meanings depending on when we evaluated it. Yeah. If this seems dangerous, yeah. Redefining names in this way changes the meaning of expressions everywhere in a program without warning. Expressions which relied on the value of a var could suddenly take on new, possibly incorrect meanings. It's a powerful tool for experimenting at the REPL and for updating a running program, but it can have unexpected consequences. Good Clojurists use def to set up a program initially and only change those definitions with careful thought. So I guess we kind of have to treat these values as global constants. Okay, so we can do something like local binding as well, but isn't let doing that already? Totally redefining a var isn't the only option. There are safer control ways to change the meaning of a var within a particular part of program, which we'll explore later. Anyways, let's move on to defining functions. Yeah, now we're able to define a named function. For example, here we're defining or binding the symbol, a variable. Here I'll say variable now. Defining the variable half and binding this to this function, which takes a single argument and divides it by 2. So here half 6, and now because we bound this function to this variable, we can call it using its name half, provide the argument 6, and it would divide it by 2 and return the value 3. Yeah, defen. Defen is a short form for doing this. So instead of writing all that, we can simply write defen, provide the name of the function, the argument it takes, and the steps or expressions it should perform. So this would return a variable which is bound to a function. Like they don't have to take an argument, but we still need to provide empty vector, I guess. Oh, sorry. It's defen of arguments, and it would simply do that. Okay, here it's a single expression and it's returning that expression, but let's see if the brackets or a vector is needed really, or yeah, it's required. Even if we don't provide any arguments, we still have to use the empty vector. arity exception, the number of arguments. Got it. Number of arguments passed to. To handle multiple arities, arities, like for example here, we should be able to use this as well as this as well as, let's say, this, and multiple arguments, which is here they're referring to as arities. To handle multiple arities, function have an alternate form. Instead of an argument vector and a body, one provides a series of lists, each of which starts with an argument vector followed by the body. Okay, here define half. First we're defining when the function or when no arguments are passed, then it should return 1 by 2. If an argument is passed, then it should execute this and return the result of that. Okay, so let's quickly define a function. Define half. If no arguments are provided, it should return this. If a single argument is provided, it should return x by 2, and that's it. I guess closed. Yeah, I have one missing. So now we can call half and half. Yeah, we can add and define multiple arguments as define add xy plus xy, add 1 2. To provide any number of arguments, for example here if we look at the function that's bound to the symbol plus, a variable plus, it can take any number of arguments, right? So the syntax that's used for providing this functionality is the ampersand sign, which slurps up all remaining arguments as a list. For example here, first define varg were variable arguments x, y, and so ampersand symbol, so it would bound all the remaining arguments to more args. So x is x, y is defined to be y, and more are more args, so it would simply return those. So if we simply call var args, now the required arguments are 2, so it would give an exception. If we provide this, then required arguments are 2, it won't provide throw an exception, and the more value ampersand more args, if they're provided, like here in this case they're provided 3 4, it would be the value of those arguments, otherwise it would be nil. We've learned about all of this in the previous chapter that we did yesterday in the Clojure workshop book. Yeah, we can, for example, when we're defining a function launch, after define and the function name, we can also provide a document string which tells a little bit about what the function does, and then we can specify the number of arguments that it takes, and after that this is the expression that will be executed. So the doc string has to be above the argument list. If it's not, if it's below it, then it would be considered a expression just like this one. And we can use doc strings to automatically generate documentation. Yeah, we can automatically generate documentation, and there's some metadata attached to the function as well, which can be extracted by calling the meta function and giving it the name of the variable. Here we're providing it the variable name launch, and it's returning the argument list, the namespace, the name of the function, column, I don't know what column really is, documentation string, the line, how many lines it has, I guess, file, which file it contains probably, or in which file it is present probably. Here the file the function was defined in, and which line and column it started at. Got it. So for example, here if it started at, let's say, this place, then this would be, let's say this is the line number 90 and the column number 1 2 3 4 5 6 7, so this would be its position. Now type, let's see how type works. Basically type just returns the type of the argument. Here it's java.lang.long. I guess it's capital L. Yeah, java.lang.long. And that type, like all functions, is a kind of object with its own unique type. Yeah, type is a variable. Let's see, resolve type, which refers to the symbol type, which has a value of this function. I don't understand the value of doing this yet, but probably there is a good reason behind it. We'll see. Or I think they tell us what the reason is. Unlike the symbol, we can change the meaning of a word for everyone globally at any time. Yeah, so without affecting the state of the symbol here, without affecting its functionality, we can simply change its type to refer to something else or to bind it to something else. Type of type is Clojure.core type. This is the memory address, and this is the namespace, and this is the reference to that type. Okay, super types. What are super types? Supers of type Clojure.lang.i object, input object, I object, Clojure.lang.fn function, Clojure.lang.asynchronous function, I guess, java.util.comparator, java.io.serializable. Okay, what is it? This is a set of all the types that include type. We say that the type is an instance of Clojure.lang.a function, or that it implements or extends java.util.concurrent.callable, and so on. We say the type is an instance of this. Since it's a member of Clojure.lang.i meta, it has metadata, and since it's a member of Clojure.lang.afn, it's a function. Just to double check, let's confirm that type is indeed a function. Okay, so to check if something is a function, we can write fn question mark, which, as we know already, question mark is usually returns a boolean value, either true or false. So if I try cats, it should be false. Returns the type metadata of X or its class if none. Okay. Type would return the type metadata if it's present, otherwise it would simply return the name of the class that the argument belongs to. Meta type namespace clojure.core name type argument list is single X column 1 added in version 1.0 static is true doc. Here's the document string, line where it is defined, and file in which file it was defined. Oh, there's also source of type. That's a neat feature. We can quickly look at how it's defined. Defn type. Here's the task string. And here's, I guess, the metadata. Metadata is defined like this. And then the argument list or the argument vector. And then the expression that is to be executed. So it would either or get meta X type if it's present. If it's not successful, it returns false, etc., nil, etc. Then it would do this, simply return the class of X. Okay, so we can type class type, which is clojure.core.type. Nice. So let's quickly take a look at the source of increment. Def increment returns a number 1 greater than num, does not auto promote longs, will throw an overflow. See also inc with a single quote. There are some metadata added in 1.2, and it simply takes a single argument. What does the dot do? Clojure.lang.numbers dot. We don't know what this dot does yet. Here they are also using the dot. I wonder if they explain it. Oh. Almost every function in a programming language is made up of other simpler functions. Plus, for instance, is defined in terms of cost, add, and reduce 1. Plus cost xy to the numbers. Cost probably costs x to a number. And here we're incrementally or recursively calling the plus function again and again with reduced arguments. Most probably, but we can take a look at the documentation of reduce. F should be a function of 2 arguments. F call if val is not supplied, returns the result of applying F to the first 2 items in call, then applying F to that result in the third item. Here it recursively calls something. Reduce 1. Okay, reduce 1 is not defined. Doc, or is it find doc reduce 1 or raw plus Huh. Is it a typo or no? It's not a typo. Okay, sometimes functions are defined in terms of others, plus uses itself twice in this definition, a technique called recursion. If you don't know what recursion is basically a function calling itself again and again until a base criteria is met. Special forms. Yeah. So basically, if we take a look at this, then plus is itself defined. For example, unlike in C++ where plus and minus and things like that are defined in the compiler, are defined in the language itself, here they're just functions which are defined again then in terms of other functions all themselves. And in Clojure, the only things that you can't divide further, for example plus, we can reduce it down to further functions. The only thing that aren't reducible further, they call those special forms. Def and let are examples of those special forms. And there are these special forms are defined in the core of the language and are not reducible to other Clojure expansions. Source def not found. Okay, some lists are written entirely in terms of a few special forms, but Clojure is much less pure. Many functions bottom out in Java functions and types or for CLJS in terms of JavaScript. Anytime you see an expression like dot, clojure.lang.numbers, add xy, there's Java code underneath. Below Java lies the JVM, which might be written in C or C++ depending on which one you use. And underneath C and C++ lie more libraries, the operating system's assembler, microcode registers, and ultimately electrons flowing through silicon. Okay, well-designed language isolates you from details you don't need to worry about, like which logic gates or registers you use, and lets you focus on the task at hand. Good languages also need to allow escape hatches for performance or access to dangerous functionality, as we saw with was. You can write entire programs entirely in terms of Clojure, but sometimes for performance or to use tools from other languages, you will rely on Java. The Clojure code is easy to explore with doc and source, but Java can be more opaque. Let's quickly review. We've seen how let associates names with values in a particular expression and how was allow for mutable bindings which apply universally and whose definition can change over time. We learned that Clojure verbs are functions which express the general shape of an expression but with certain values unbound. Invoking a function binds those variables to specific values, allowing evaluation of the function to proceed. Functions decompose programs into smaller pieces. Yep. And we can learn about the Clojure functions using doc and source. And yeah, that's it. Basically, almost all of it we learned yesterday as well. Probably this wars things is new, or it's not really new, but it's explained in a different way, and I think this made it more clear what wars are and what's the difference between a symbol and a var. And we also learned about this more syntax, For example, to provide any number of arguments, there's this ampersand sign. And besides that, what else did we learn? We learned about meta and how type works and supers and function, and how to look at the source code of type of variable or function. Yeah, that's chapter 3. Should we quickly go over this chapter as well, or should we first try to solve some problems? Let me just quickly log in. Did we learn about sequences, map, filter, lost element, element, local bindings, nth element? Yeah, let's try to do these. Intro to sequences, sequences rest, intro to functions, double down, hello world. Okay. The Clojure collections, all Clojure collections support sequencing. You can operate on sequences with functions like first, second, and last. So here first would return 3, second would return 3, last would return 3. And here we first were running it on a list which was defined using this syntax, single quote, and in curly braces 3 to 1, or in parentheses 3 to 1, and then this is a vector, and here we're defining the list using the list function 1 2 3, and all would return 3. Yeah. The sequences rest. The rest function will return all the elements of a sequence except the first. So here rest would return everything except this 10, so 20, 30, 40, and it would return it as a vector. I wonder if it's vector, it would return it in a vector. Now it would return it as a list still. So let's be explicit. This would be a list, but we know that 2, 3, and 4 is equal to 2, 3, and 4. So I guess it doesn't really matter that much. Okay. Two, 3, and 4, isn't it the same with Clojure compare list and vector? Quality. Oh yeah, we have to define it like this. Yeah, my bad. So this should, yeah, this is a list. And then Clojure has many different ways to create functions. We've learned about this one. This is a named function fn add 5, which takes an argument x and adds 5 to it, and we're calling this with the value 3. But I don't think we can use this name later on. Example, yeah, but can we still no, we can't. So we have to use defn or let for that. This is an anonymous function which takes single argument and adds it and calls this on this, and this is a shorthand for the same function. Here we're adding the first argument and 5 together and calling this on 3, and we haven't learned about this yet. So partial plus 5. Let's where is unmatched delimiter? Yeah, partial plus 5. Can you provide multiple arguments? Dot partial. Okay, partial takes a function f and fewer than the normal arguments to f and returns a function that takes a variable number of additional arguments. When called, the return function calls f with arguments plus additional arguments. So it would call 5 plus. Yeah, this is the function, this is the argument, and it would call it on these additional arguments as well. Okay, it takes a function f and fewer than the normal arguments to f. Yeah, normal arguments to f. Okay, and returns a function that takes a variable number of additional arguments. When called, the returned function calls f with args plus additional arguments. So here it would call 5 plus 3, which would be 8, and then it would call 8 plus 2. Yeah. Now double down, write a function which doubles a number. So you can use this simpler syntax, or yeah, let me try this partial syntax because I want to see how it works. If we try partial times 2, and then if given 4, it should return no, if given 2, it should return 4. If given 3, it should return 6. Yeah, so let's go with this as well. I should comment it out, and I want to use this syntax. We can also use the defn one or let one or anonymous function as well without this shorthand. Hello world, write a function which returns a personalized greeting. Hello Dave. It should. So what I'm doing is, it is taking a single argument. This is a shorthand and this is the argument, so we're just simply concatenating the strings together. String hello comma space, here the name that is passed, this is Dave Gem, and then at the end append the exclamation mark. I wonder if we can use partial for this as well somehow. Let's try partial on the function string, and this would be hello, and yeah, how to get the first argument here? Would this work? I guess not. I don't think this would work. So if we give it Dave, Yeah, this won't work. But yep. So if we do this, then it would work, but this would change the syntax of provided here. So yeah, let's go with this one as for now. And double down, hello world. Now sequence map, filter, lost element, penultimate, local bindings, nth element. Let it be. Count a sequence. I will do these. We'll do all this, inshallah. Okay, sequence is map. The map function takes two arguments, a function f and a sequence s. Map returns a new sequence consisting of the result of applying f to each item of s. Do not confuse the map function with the map data structure. Okay, this is the map function. There's also a map data structure which we've learned about previously, and a syntax I've completely forgotten about. Let me go take a look at it real quick. How are the maps defined? Maps. Yep. So any two value pair A, B, C is defined to 1 and 2 and B, D, F, and it's 3. Yeah. Okay. Now we remember. So this is the map data structure and this is the map function. Here they're talking about the map function. Map function takes two things, a function and a list or a sequence, and applies the function on each and every element of the sequence. So for example, let's try to apply, let's quickly create a function that multiplies something with 2 and give it a sequence of 1, 2, 3, 4, 5. So it would return, this is 1, 2 multiplied by 1, 2 multiplied by 2, 3 multiplied by 2, 4 multiplied by 2. So it would execute this function or call this function for each and every one of these sequences. Okay, so here we're adding 5 to it, so 1 plus 5 should be 6, 2 plus 5 should be 7 and 8. Instead of doing this, let's just, for the sake of variety, let's use this. It's the same thing, just I just want to reinforce my learning as well. Filter. The filter function takes two arguments, a predicate function f and a sequence s. Filter returns a new sequence consisting of all items of s for which f returns true. Okay, so this would always be filter function. Okay, so this function, this anonymous function, should always return either true or false, truthy value or a falsy value. And the filter would return all the sequence or all the elements in the sequence that are true according to this function. So here the function that we're evaluating is if the element is greater than 5. So 3, it should return false, 4, it should return false. So in the end sequence, the only thing that should be returned is 6 and 7. Okay, last element. Write a function which returns the last element in a sequence. I guess we can also do lost. 1 2 3 4. Yeah, we can do lost as well. Let's try first lost. Oh, my bad. Should simply be lost or lost. Okay, yeah, special restrictions lost. Got it. So we don't have we have to do this in a way that we don't use lost. So one way is to I don't know when did I do this. Let me quickly see what does comp do. Comp take a set of functions and returns a function that is the composition of those functions. Okay. So it returns a function that is a composition of this function. So here we're reversing this string and then using first on that. Okay. Is there any other way we can do this? Without using lost? Yeah. We can try to use the nth keyword. So for example, let me see what nth is a function. Yeah, returns the value of the index. Got it. And how to get the count or size. Yeah. Okay. So we need to nth takes column and an index. Column needs a collection and takes a collection and an index. But here we're not providing an index. Okay. This should work. Okay. But is there another way? I bet there is. I just have to think hard enough. We can count. Yeah. For example, if I count, there's 1 2 3, it would return 3. And if I count 1 2 3 4, it will return 4, and we can use that value to access the list 2 3 4 5. So it should return won't be able to quickly, for example, get the value at some specific index using this, or was it the other way around? First sequence and then the index. Yeah, it was the other way around. Let's look at a couple of solutions and see. Yeah, there's an nth solution. Okay, we need to provide a function and that takes an argument this and then decrements count by that Okay, yeah. Yep, I was thinking of doing this. Or first, we'll just take last one. Let's look at take last. Returns a sequence of the last n items in column. Yeah, got it. So it returns a sequence. So if we do this, for example, take last, specify how many items we want, and then give it a function or a sequence, then it would return a list, right? But what we want is a single element, so we can take first of that and it would return the last element. Yeah, that's a clever solution. And this is a complex one. Wow. Okay. That was, yeah, let's quickly add the nth solution here as well. So we need to return the nth value of the sequence